What is a line integral, and why should I parameterize it?
Vectors! Vectors everywhere!
A line integral is a multivariable integration along a given curve in space. We parameterize them in order to reduce the integration to a single integral in 2 dimensions.
Line integrals can be used to find the work along a given path, determine the mass of a wire, or determine the strength of the magnetic field around a conductor.
Basic shapes to parameterize include circles, ellipses, and lines. I'm the Batman.
And curves. The first step in computing a line integral by parameterization is to parameterize the path in terms of a vector with a single variable, r of t. You're going to want to determine whether or not the function is a vector, and also whether the integral is in terms of ds or dx, dy, and dz.
If you are given the function in terms of a vector, take the first derivative of r of t and then integrate. If you are given the integral in terms of dx, dy, and dz, simply take the first derivative of r of t and then input values for x, y, and z respectively. Subsequently, integrate the resulting function. If you are given the integral in terms of ds, simply convert ds into dy, dx, and dz using the formula on screen. And now, this.
Problem right here. Now, it's this integral where c is the right half of the circle x squared plus y squared equals 16, rotated in the counterclockwise direction. So first of all, we want to take a sketch of c. So let's see. We know we have a circle, and we can tell by this the radius is 4. And we want rotated in the counterclockwise direction, so that is positive, going this way, and the right half of the circle. So our limits for integration are going to be negative pi over 2 to positive pi over 2. Alright, so now that we have this, we're going to want to write a parametric equation to represent this. And that's going to be, it's going to look something like this. So x of t, y of t. Alright, so since this is a circle with radius 4, we know that the parametric equation for a circle is going to look like this. And that's just something that we know. Alright, so let's get to the integral over here. Now ds may look unfamiliar. ds is defined as the square root of dx dt squared plus dy dt squared dt. So, in order to get dx dt and dy dt, we take a derivative over here of these. So, that will mean dx dt equals the derivative of 4 cosine of t, which is negative 4 sine of t. And likewise, dy dt equals 4 cosine of t. And that's just by taking the derivative of this. So now, we can solve for ds by plugging these in. So we'll get ds equals the square root of negative 4 sine of t squared plus 4 cosine of t squared dt. Now, we can simplify this quite a bit. So this is equal to the square root of 16 times the sine of t squared plus cosine of t squared. Trigonometric identity, that is 1, as you should know. So this all equals 4 dt. And there's a dt over there. So ds, by plugging into this and this, is equal to 4 dt. So now that we've got this part of the integral done, we're ready to parametrize the entire thing. So we can write this as the integral of xy to the fourth ds equals, and what we're going to do is we're going to plug in x of t for x and y of t for y. And instead of c, we're going to put our limits of integration here, which are, because this is this half circle, negative pi over 2 to t to pi over 2. So we have the integral from negative pi over 2 to pi over 2 of 4 cosine of t times 4 sine of t to the fourth. And then our ds, which we solve for over here, is 4 dt. And at this point, this is a simple Calc 2 integral, and you should all be able to solve this.
A real-world use of line integration is Ampere's law, which states that for any closed-loop path, the sum of length elements times the magnetic field in the same direction is equal to the permeability times the electric current enclosed in the loop, or simply this.
Using the variables from the figure in the last slide, the enclosed current is simply the initial current times the sum of the circumference squared minus the inner radius squared, okay, all over the circumference squared minus the middle radius squared. B is the magnetic field strength and is usually a constant. ds is the change in circumference. Since the cable is a cylinder, this area is given by the function we all know and love, 2 pi r. Therefore, the integration becomes the formula that is listed on screen. Now, obviously, I skipped the actual line integration, but time is limited, and this is how you would do it in the real world. Because, in the real world, you have resources.